A slight bit of background here. I'm coming from a different user space than most of you here. I normally work for the past decade in Java and web services, microservices, that kind of stuff. It's an area where the D programming language is not very much used, but I think that's actually not something that's going to be like that for very long. I think we're kind of at a moment where we've had a lot of businesses entering a market, and efficiencies and cost saving is going to become increasingly more important. And this is something where I think systems level languages like D are going to have an increasing impact. All right, so what am I going to talk about briefly? Just for those of you who've not worked with microservices and web services, just explain what it is. Talk about some of the applications of system level languages that are unanticipated, why D makes for a particularly good choice, and then go through some practical examples of how this can be done end to end, including things like deployment and all that stuff that you use for putting a service up alive, and then some concluding remarks and a summary. So let's briefly summarize what are microservices, what do they do, that kind of stuff. The brief bit about it is that when you have a large company working on something big, whether it's Netflix or eBay or whatever it happens to be, you have a lot of people working very quickly on a lot of different projects, and they're all working with their separate deployment schedules on top of each other. You have zero allotments for any kind of downtime whatsoever. And working on a system where it's all one big software piece is very difficult because maybe someone has a problem, they can't deploy code because there's a bug. Then another team, which is working on an unrelated part, is completely shut down. So microservices are a way of breaking apart your code, not just in actual different code bases, but in terms of how people work on the code as well. So it's a variant of what they call service-oriented architecture, and the gist of it is that you have a bunch of independent programs that are running on a service. And they typically have a web interface for synchronous communication. So they arrange the way URLs access these servers, like API post, then add post, or something like that. And this REST communication, the synchronous one, can be over HTTP, typically using JSON as its body, but it's not required to be JSON. There's some other mechanisms, like there's the Google RPC protocol, which is used for synchronous communication. And then you have non-synchronous communication. You have asynchronous communication. This could be something like accepting a task to be done and get a result later. Like, I want my bank statement, but then give it back to me in a couple minutes or so. And there's different technologies for this. You could use Apache Kafka or Apache Pulsar, RabbitMQ, Amazon Web Services, SQS. There's a bunch of them. So you basically have synchronous communication, send a question, get an answer. Asynchronous communication, send a question, maybe you'll get an answer later on. And each service these methods of communication are typically standardized within a project or a company. And then you have individual services with specific tasks, whether it be giving a loan or something else. And each one is focused on doing their own thing. It's because these protocols in which they communicate are not necessarily hard or language specific, like an HTTP URL with JSON data. These services don't even have to be implemented using the same technology. So you can actually be free to experiment. One service in Java, another in Python, etc. So you might have something like you have users on the outside reaching you from the internet. You have some sort of gateway system. Every single time you have a web service, you always have to deal with massive amounts of people trying to defraud your system, especially if there's a reason to attack your system, like if you're building a bank and people think they can steal money by going to your system. So you may have a way of doing denial of service, a firewall, etc. And then once you have these APIs, different URLs will map to different services. So in this case, someone was saying going to cards and setting the PIN number for a card. Well, your gateway system may recognize that prefix of the URL, cards, right here, and it basically may route that traffic and say, aha, this goes to my credit card service, and it sends it down that way. Or, and this service, of course, may do something different. It may publish an event, like someone is actually working from MasterCard, and MasterCard sends an update that some transaction has been made, and then it tells the rest of the system, hey, I'm publishing a transaction event. And then different services can react to that. And this here, you have a publish subscribe system. So the account statement service may react to that transaction, add it to your next monthly account statement, or you may actually have the user transaction history. If I want to see the list of my transactions on my account, that service will update itself. Each service may have its own database, etc. So that's a typical example of what microservices look like in a small application. So why bother? Why even do things this way at all? It has a lot of advantages. One, you can have different people working on different technologies. You can experiment with new technologies and technologies that are hard to use but have a good payoff like performance. You can actually deploy on a service that is performance critical or something like that. It also decouples the work from the team so that the teams can actually work on independent things without actually interfering with each other so long as they meet their interface. And it helps you document in your system because it gives you clear contracts of what is each service responsible for doing, and it's easier to test whether an individual service is right or wrong without having to look at the entire system end to end. And it basically allows you to isolate where you spend your work. Like if you have a bunch of read load on one system and a bunch of write load on another system, you can work on them in a different way and not necessarily apply the same optimizations everywhere or even replicate them on different servers the same way. You can choose by service how you want to do your optimization. And such architectures are the norm for a lot of businesses. So most web-based services that you know of, like Amazon, eBay, Netflix, Spotify, this is typically how they operate. Okay, but they're not free. Nothing's free. So what typically happens is because instead of having one application with different sets of business logic, which may have been contained in libraries before or multiple processes on the same computer, I'm having them deployed as like actual separate servers. Well, this normally can mean that you actually have a separate computer. If you have your own infrastructure or on the cloud, you can have separate computers there, and they're not free. So in this case, in Amazon, there's a machine type called M4X large, and it costs about 20 cents per hour. So if I have a service split behind a load balancer and there's 3 of them, you're paying for 3. That's 60 cents an hour, and it adds up very quickly. So one of the things that have been going on since like the 2000s and 2010s is a way of kind of cutting cost. Sometimes a service doesn't eat up all the resources of a computer. You may have like a 4-core, 2 gigahertz CPU with 16 gigs of RAM, but you don't need the whole thing for every service. So you can use container orchestration systems, like Docker is a very common one. And the idea is you can allocate how much resources do I want, and you could potentially let each service run as if it was on its own computer, but it's not. They're actually using up a fraction of the computational resources of a single computer. So one of the advantages of this approach is that you can save a lot of money by using only as few computers as possible. Because when it comes to billing, you're typically paying for entire computers, whether you're using it or not. So if I'm only using half the CPU and half the RAM, might as well put 2 services on it. Oops. Now the thing about it is, there's several types of pricing that matters, that influences like how much you're going to spend on this. Some of it is you can save, some of it you can't. So there's the hourly pricing for computers that have like CPU and RAM. That's kind of a cost for the bigger machines you have. You can have different costs. You're charged for disk space, network bandwidth, public IP addresses. This is kind of like a head tax almost, like a cost per computer, because each computer could potentially have its own public IP address. And then if you have how many people are attached to your load balancers is another cost that comes up. Load balancers are really important because in web services like this, you're almost always dealing with situations where there's far more connections that any computer can actually handle, and you have to split up your traffic, otherwise your system's gonna fail. Like you start running into problems of like, there's limitations on your network that come up in unexpected ways. Like you can have so many incoming new connections from random people around the world that your operating system fails because it has too many open file descriptors, because you can only have a certain number of files open in your operating system at a time. And if you have enough incoming TCP connections, you can overrun this limit and actually have your system die that way. Now, in terms of saving the cost, the savings aren't as good as you might think from combining services onto one machine. Here's some of the pricing tables for some of the computers that you can have in Amazon, and look at this, for example. We have, for one virtual CPU with 2 gigabytes of RAM, it's costing roughly 3.6 cents. Well, if I double this to 2 virtual CPUs and 4 gigs of RAM, it costs about double. So that means having a bigger computer and running multiple services on it didn't really save me as much as I thought, because I could have gotten 2 smaller computers for the exact same price. I am saving on some cost, so I don't have to have 2 separate public IPs. I don't have to have a separate load balancer. So I'm only really saving when I'm not really using the resources on my computer. But if I'm fully hitting everything I have, if I'm fully exploiting my resources, the price difference between 2 smaller computers and 1 bigger computer isn't as big as you'd think. So this kind of brings in the next topic. Typically, when you have web services, they're written in languages like Node.js using JavaScript, you have Python, you have Java, and a lot of these companies were essentially first to market. They're doing like the first online bank in their market, or sharing of videos, or a music recommender system, and they don't really have much in the way of competition. But as industries mature and there's multiple competing people, the ones that can actually cut their cost, which can often translate into lowering costs for their customers, have the competitive edge. And this is something where it's not happening too much these days, because often the engineering costs are considered to be paramount and the most important thing. But these costs are not to be ignored either. And I've seen some pretty extreme examples where like even single services for a company will cost over $100,000 a month just to keep up with the traffic that they have. So the idea is that you get what you pay for. Cloud computing platforms like AWS have become quite efficient, and 2 1 CPU computers can cost roughly as much as a single 2 CPU computer. So the savings that you thought you were going to get from just bundling everything onto one computer aren't as much as big as you might think. And for large companies, you can end up in situations where 10 to 100,000 US dollars per month is not uncommon. So any amount of money you can save just out of sheer scale ends up being a lot of money, like translates into you can hire more engineers for this amount of money that you're saving. And then for smaller companies, there's also an appeal for efficient services, because with small companies, you don't have that much money. So if you don't have that much money, any little bit that you can save actually adds up pretty quickly. So the idea of using a system level language is waste not, want not. If you don't actually use a bunch of resources for disk and CPU, et cetera, you don't have to pay for them. So just as it looks like you could get a benefit from having multiple, let's suppose my service needs the equivalent of 1 CPU and 8 gigs of RAM, and the computer I'm running on has 2 CPUs and 14 gigs of RAM. Yeah, I can get some savings by having 2 services right on here, but if I could solve the same business problem using less resources, I can also get a lot more savings, just as much as I have by bundling services together in this example. So the idea is that you don't use as much resources when you have a language that's efficiently and directly compiled to machine code, instead of like running through an interpreter like Python, JavaScript, or Ruby, or running through a virtual machine like Java, Scala, C# and Erlang. So system level languages can get a serious advantage to do the same work because they're compiled directly. So there's 2 ways of looking at performance. You can say, this is my computer, it's like a Nintendo Entertainment System or something. I want to get the most powerful game as I can out of this piece of hardware. That's one way of looking at performance. The second way of looking at performance is, I have a given business problem. How can I solve that as cheaply as possible using as little hardware as possible? That's the way of looking at efficiency that matters to these big web service companies. So this leaves room for languages like D, C++, C, Rust, Go, Ada, Fortran to actually have an impact if they can solve these business problems. So kind of a practical example of looking at D versus Java. So having just a minimal web service where you give it some data, it does some transformation on that data, and then spits you out a result using a REST interface. So HTTP call and send it something, get some data out. The request you can get per second using Java and the Spring framework I found to be about 5,200 transactions per second, which is pretty good, although the memory usage is quite high. So the Java program used about 10 gigs of virtual memory in this case, and resident memory about 280 gigs. And the exact same algorithm, doing everything the same, using D language and the vibe.d framework from Zonke Ludwig. There, it's a much smaller amount of memory, less than 5% of the RAM being used, a fraction of the virtual memory, and about double the performance in terms of raw transactions per second. Now, of course, you're not granted to have everything translate this cleanly, but this is just a smooth, tiny little example of how even such a small thing as the programming language can have like significant impacts. I mean, in this case, it's 100% difference in terms of output. Now, there's reasons why people aren't doing this already, because if it was all just peaches and cream, everyone would already have done it. The reasons why they're not doing it is because systems level languages often are very complex, and you end up paying a lot in terms of engineering time to get a program actually working, debugging errors, that kind of stuff. There's often a lack of libraries that are critical for solving certain problems, whether you're communicating with AWS or Kafka or working on machine learning. So the availability of libraries is a strong reason to pick a programming language. And then one of the traditional problems with programming languages that are compiled is they had to be specifically compiled for the machine. So if I have 5 different types of machines that I'm running on, you have to compile them 5 different times. And that was a nightmare for like software that runs like on a desktop, for example. So I think Java got really popular on the motto of write once or compile once, run anywhere, which was really big when there's so much different types of hardware out there. And then, of course, for languages, especially C++, the compilation times can be quite long compared to that of like an interpreted language or a language like Java, which compiles for the virtual machine. But this varies considerably language to language. So why D? What makes D so special in this kind of race? Because there's a lot of competition. So the obvious advantage is that D is a system-level language. So you can get it to run much, much faster than you could, say, Java or JavaScript or Python. And D happens to have a syntax that's very familiar with anyone who's worked in a C family language. So not only that, D is especially good at incorporating libraries from other languages. This is something that is fairly unique to D. D has chosen to have a very broad range of features. It's iterative, it's functional, has object-orientedness, it does all these things. And so if you're trying to pull in a library from another language, like perhaps my previous implementation was in Python, and now I need a Python library, you can almost mechanically convert those libraries because all the features that it depends on already exist in D. The same thing is true with C++, with the exception of multiple inheritance and a few other things. But D it casts a wide net, unlike a lot of other languages. And one of the other things is that D is very good for prototyping. So I mean, I know not everyone's a fan of garbage collection, but what it does do is that it really reduces the amount of time you spend working on things. And for web services, the latency penalty you pay from time to time is not that bad. And you have to think about it. A lot of these environments, like web development, like it takes time for messages to go across the internet. So if you add, worst case, 10 milliseconds to a request, which the user can't even perceive it unless you're at like 100 milliseconds, it makes almost no difference. And the near ubiquitous use of Java proves that case. They don't care about the delay or the latency from garbage collection. So the benefits seem to outweigh the cost. And of course, D is especially good when it comes to error detection. So you can quickly add unit tests, you can have preconditions, post-conditions, and knowing that your code is working correctly, especially as you're converting libraries, is a big deal. So there's challenges to using D. So imagine using a language like Java. You're not going to get everything you want, and overcoming these challenges are kind of important. So D doesn't have a super strong IDE integration, especially not compared to things like IntelliJ's IDEA editor, which has like very deep understanding of the Java virtual machine, has very powerful debugging tools. Sometimes when you're looking at critical performance problems, there's a lot of visual-based profiling and memory tools. Java has extremely powerful tools for this. And we're going to talk about getting around some of these limitations in a bit. And then when it comes to certain domains, there's just not libraries that exist in D. So integrations, like for example, Amazon has not made integrations for the D programming language. They have for Java, they have for C++. When it comes to database ORM libraries, D has some, but it's somewhat limited in their ability. Rule engines, so businesses have tons of places where they just need arbitrary rules that have to be managed by someone in business using a spreadsheet, for example, and having a way of integrating into your system is something that there's not a good library for just yet. And then a lot of security access systems. So I think HashiCorp has a system called Vault, and like many of these corporate systems, they don't necessarily recognize D as one of their main usages, so they don't necessarily have libraries. Now, how do you overcome some of these challenges? So when it comes to IDE integration, there's actually quite a few good stuff out there. A member of the D community whose alias is WebFreak has done an excellent job. He's done excellent work at integrating D into, I believe this is a tool from Microsoft, Visual Studio Code, but they've actually published quite a few open standards for basically interacting with an IDE. One is called like LSP, Language Server Protocol, which allows you to integrate things like code completion, documentation, lookups, and if you write something compatible with LSP, it can work in more editors than just Visual Studio Code. For example, the same code completion and highlighting and documentation lookups that you can get that work through this plugin with Visual Studio Code, you can also use those in Emacs, for example, and get the same benefits. Now, it looks good. It's a very professionally made editor. The biggest weak point at this point would probably be because it's based on debugging integration with GDB and LLDB. And these have a few problems with evaluating expressions. Like if I'm running through code pause and I need to, here's a piece of code that I know that's broken and I want to try out, type in by hand a few variations to see if they also produce a similar error. It doesn't have full access to the symbols inside. And sometimes viewing class members when you're hitting a breakpoint can have a bit of trouble. But these aren't unfixable problems. This is just how it happens to be right now. So it looks like this. This happens to be a debugging session, and you have like a nice, smooth-looking piece of code. You can pause. You can see what's going on. You can print out breakpoint information. This is that example I was talking about here. If I tried to print out a data member, and it says data service does not exist in the current context, that's fixable. You can see what are the variables that I'm watching, and you can click and point with it and debug in a nice, very comfortable fashion. If you prefer like more, also, one of the downsides is that the configuration from your system, you kind of have to, they give you a template and you have to edit it by hand, and it doesn't have automatic detection of your project's configuration. Like, if you compare to tools like Java's IntelliJ, their equivalent of their dub file is based on tools from Maven or Gradle, and the editor will detect what you have, the structure of your project, and build your project's configuration for you. So you just have a small file you have to edit so it knows like what's the name of your binary file, where's your source coming from, a few other things. What command line arguments do you want to give it whenever you run? But that's it. You set it up once and you're done. Please, go ahead.
For the configurations, since the latest code D release, there's actually the implementation, so it automatically builds for you and detects the debug configuration. Inside the user guide, there's a page on that. It's still not fully complete, but it's a nice start.
No, so that's excellent. Sounds like things are just getting better every day. If you prefer kind of a more like responsive user interface, because I'm one of those people like, I don't know, I can sense those millisecond delays when I type, so I prefer to work in Emacs myself. But the tools are still there. The same integration that was built for Visual Studio Code based on the language server protocol, they can be integrated with Emacs and you can work. And this is an example of doing the similar debug session on the similar code where you can actually see your breakpoints over here. You can type in arbitrary commands here. You can watch variables and keep track of your breakpoints. It's not as pretty as Visual Studio Code, but it works. And it's fast, which is the important thing. Oops. All right, now profiling. How do we overcome some of those challenges? There's different tools that are out there, and I guess there's more than one way to skin a cat. One of the ways of actually doing memory profiling or performance profiling is using the tool Valgrind, which those of you who work with C++ are already very familiar with. And the D-Wiki has a lot of really good instructions on how to do it. So there's this tool called callgrind, which basically keeps track of the function calls, how much time is spent on them. And you can combine it using a tool called kcachegrind. And this lets you visually look at the data that comes out. And you end up with like a pretty graph like this, where I can basically I can look at my project, I can look at what's being called, where my time is being spent, and I can get a % by function, including just the time spent on the function itself or the time of everything it called within it as well. You can get a nice visual graph of where that time went. In this particular case, when I was profiling my program, I found that validating JWT tokens took a lot more CPU than I thought it would take. Now, memory profiling. Memory profiling, there's a compiler option called profile equals GC, which is just built in with DMD, and you can use it right out of the box. There's no visual tool that comes with this, but what you do get is nicely described data. You can see the bytes allocated, the number of allocations, the type, the function. So if you're trying to figure out, am I losing too much time because of garbage collection or whatever, instead of just saying, oh, it's slow and cursing the garbage collection, just look, see, are you actually allocating memory? Where is it going? Where are your hotspots? Sometimes just a few changes of your code solves 90% of your problems. And this one works pretty well. It's not as good as what you can get from other systems. Like in Java, for example, there's a tool called Visual VM, where you can actually attach to your program and you can get a visual map, just like we had for the CPU profile. You can use in K-cache grind. They can do the same thing for memory. However, the raw data is there, and it's just a matter of time before, or an effort when someone makes a tool to let you visualize the memory tracking in D as well. Now, at least based on my own testing, I tried using CPU profiling using the dash profile tool. However, I would not recommend it at the time because when I turn on the profile switch, I find I have problems even compiling my program at all using the standard library. I also have problems with the performance being impacted pretty heavily, and the output format often doesn't come with headers, and so it's not clear what it means. But the fact that we have tools like valgrind and K-cache grind, yeah, please.
I gave a talk at the last DConf online about profiling and one of the valgrind ecosystem, along with heap track and some of if you want Intel, you can use vtune. They actually can give you a graphical overview of the memory allocations.
Oh, that's fantastic.
It does work, and don't use dash profile. It's terrible.
I think it can.
Profile GC is really good. Profile GC is extremely useful.
Yeah, Profile GC is very good. Profile can be made useful with a bit more documentation, I think. That's all it needs. Just a little bit of description of what the columns mean, which I cannot find on the DLang webpage. I think there is a digital Mars webpage that has a description of the information, but yeah, it's a bit too hard to struggle with. Okay, now there's certain, let's see.
The reason there's no documentation on it is it's trivially obvious to the most casual observer.
Okay. Now, when it comes to doing things like library coverage, so library coverage is a big deal, and like library coverage is often the reason why people go to a programming language. If you're working with data science, if you're working with statistics, and you want to use NumPy and SciPy, you're going to be using the Python language just because a lot of the people you're working with make great tools in that language. Now, when it comes to the kinds of features different languages have, D happens to have a lot of these features. So if I'm importing a library from Java, for example, and I don't exactly know how the memory allocation works because Java has garbage collection, well, so does D. So importing a Java library is no big deal at all. You want to do raw pointer manipulation, but there's some weird algorithm that a C++ library has, you can do that in D. I mean, you may have to make your code trusted, but you can do it. You have an object-oriented system, you can do that. Well, as long as you're not Go, but you can do it in D. You want to do generic templating-based programming, you can do that too. You want to just have like some quick prototyping, try out a piece of code, see if it works without having to like spend a lot of time configuring and building everything. D's got you covered. D happens to have such a broad feature set that pulling in libraries from other languages takes, I would say, comparatively a lot less effort. So when you're converting libraries often tend to be big. We're talking like 50, 60, 70,000 lines of code sometimes, and it doesn't take many bugs to basically ruin your efforts. And so you want to minimize the number of moving parts when you're converting libraries. So first thing you want to do is, I have a big piece of code. You want to understand the chain of dependencies. What are the deepest things that nothing else depends on, and convert those first. These are usually utilities, data structures, that kind of stuff. And then the next step you typically do is convert the library with as little changes as possible. Because every single time you see something and you're saying, this could be made more clear, this could be more simple, you're going to pay for that because everything that depends on that is now going to have to be modified. So a straight up literal conversion often saves a lot of time.
I've done a lot of work porting code to D, and it's not possible if you don't have a test suite.
Exactly.
And the way to convert the code is you convert one module or one file at a time, and then you get it to pass the test suite.
Exactly.
And if it doesn't, and you want to track it down, you go down to converting one function at a time, and then pass the test suite. And what that does is, when it doesn't work, you have only a very small amount of code. You have to look at it to see where it went wrong. And I found this to be a very successful approach. What does not work is trying to port the whole thing at once. You'll wind up with an unworkable program, and you'll have no idea why.
Exactly. And this problem is compounded even worse if you don't understand the material that you're converting. Maybe you're not an advanced PhD statistician, but you need that statistics library. So being able to mechanically convert a library just based on the language syntax alone without even necessarily understanding the concepts behind it is possible when the language supports all the features that you're migrating from. So here's like a little tiny example of one of the things that becomes a little trickier. So this is from a C++ library, and it has this function seek2. And it's iterating through something that has a range iterator, and it's referencing the previous element and the next element. The rest of the code is irrelevant, but the fact that it's taking a data structure and kind of looking in both directions, this is actually a little bit hard to do using the standard library in D, because the standard library in D is built on ranges. And this is effectively not much different from looking at pointers. So getting some random pointer and then crawling in both directions in memory, not so easy to do. So that's something that you often need a way of solving, which I'll get to in a bit. Here's another little example here where it's another algorithm from the S2 geometric library. And what they're basically doing is they have this next element and their last element, and they're starting from a range of values, and then they're kind of incrementally squeezing towards the middle until they reach a meeting point. Such algorithms not so easy to convert in D, but the way around this that I found to be most effective is, I mean, the nice thing about these generic container structures like maps and all that stuff is you can just get a textbook on how to do them. So I happen to be working on a btree, which is used for databases, and I had implemented it with a range interface. Well, I just added on top of it some iterators. So I could actually use it in my C++ code to convert it over with very little effort. And not having to rewrite the core algorithm itself made it far easier to convert the library. So that's one thing I would recommend. These are all available online. It's an open source project. So when we share the link for the slides, just click. If you happen to want to borrow this code, go ahead. So putting it under practice, how does this all work in real life? It's all good in theory and all. So let's introduce a practical problem that we'll talk about. So let's look at some industries. We've got ride-hailing, micromobility, Internet of Things, and sensor monitoring, military, security, situational awareness. What do all these things have in common? They all have high volumes of data, and they're heavily write-heavy. They have lots of data updates, and there's a lot of queries for this data in real time. So by the numbers, let's suppose we have 1,000 taxis per city, and think of something like Uber, a ride-hailing app. We got 50 cities. We got one position/status update every 10 seconds. We're already at 5,000 updates per second. This is something that will kill most servers. You have to have a distributed service to solve these problems. And then you maybe have 10 million people per city. 5% of users even look at the app per day, and maybe they're looking at it for a little while, and you end up with 5 queries per user session. In this case, you end up with 1,500 queries per second. So these are numbers that are like quite hard. This is a heavy performance problem, and designing a traditional system using databases can end up getting very expensive. So you have this dilemma where customers want flexible queries. They may want to look for cars of the economy class, or they have more than 4 seats in them. Whatever their criteria is, you have a lot of queries that are arbitrary. So the queries you could solve using an RDS, but the write load is extreme. And when you're writing data to a database, the writes can be a limiting factor. Yes, you can have read replicas, which helps you on the read side, not so much on the write side. You can have sharding, and then you can imagine as you basically build your system, get it more and more complex, you need more and more computers, and that costs a lot of money. So one of my most recent projects is I've created a company called Funnel Labs to basically take on this challenge using D, how to solve it. I want to give you a brief look of what this looks like. In fact, I'm not sure, let's see if it works. So this is not this is just a JavaScript wrapper. It's the server that's the actual system, which we'll talk about in a little bit. So this happens to be looking at data, and we have these fake cars, and these cars have this little data which you can see in JSON. This car happens to be inactive. Its ID is myfleet number 8. There's an age field called 48 and a coordinate. So what you do is you give an arbitrary thing. I could say coordinate is within 1.5 kilometers of this location, and I can add restrictions. It's like an SQL-like language. So I can say, and status is equal to inactive. So now I only get the gray cars. And if I want status to be active, as an example, then I only get the black cars. This is just a JavaScript client, but the real system that's built to handle the load, you can imagine this being like a bunch of taxi drivers that are uploading information, and then this is the kind of view that a user would see. And of course, everything is driven by an arbitrary schema. This schema happens to be written using Apache Avro. So any customer with any client, whatever their data format is, they can just specify what they want. And in SQL, in a relational database, you may define your data schema and then what indexes exist. This one's a little different. Your data is described using JSON. In this case, I have that field ID. ID is a string. Oops. And then when I want it to be indexed, I just add a JSON attribute. This is a primary index. This field is an equality index, which means I can do this field is equal to this value comparisons. And there's also a comparing index, and then there's a special type called a spatial index. And what a spatial index does is it powers these things like spatial is implied to be on the surface of the Earth. So I can say things like within 1.5 kilometers of a given latitude, longitude coordinate. And you can combine them using and, or, whatever. But the point is this system is basically built for load. It's built for speed. And the D programming language is to basically make that possible. So, oh, I lost what slide I was on. There we go. So how do we actually make this happen? So first, let's talk a little about to the user, the client, the business that wants to use this system. What does this look like? So you want to protect your system. You can't just have any random person on the internet accessing it. So it's using JSON web tokens to where you have to authenticate using a username and a password over a secure HTTPS session. And what happens is you upload an arbitrary schema, whatever data format you want. And then without having to do anything or recompile or whatever, you can start uploading data immediately. In this case, it's uploading a person who's a waiter, and it's a new data point. Then you can just start executing queries. Just spit out the data and query immediately. And what the system essentially does is it's getting its performance because it's not doing some of the things a database would normally do, like writing things to disk. It's meant for real-time data. Like if I'm looking for a taxi driver, I care about where are they right now, not 5 minutes ago. So it's basically built for modern data. So the structure is essentially built where data comes in mass, it's split through a load balancer, and there's these systems called the mouth. It's like the structure of like a physical funnel. You have like that cone-shaped part, the mouth, and then you have the stem, and then the spout where you read where you actually like get an output. The mouth is load balanced. It cares about having enough network connections to receive all the information, and then it bundles it up into these piles of data. Because every single time I go up and down the network stack, that costs CPU, that costs system resources. And by avoiding that, by bundling messages together, let's say 1,000 at a time, then I can actually do mass data updates without having to pay the cost of going up and down the stack, reading from the network. Then, of course, I load balance the data across this third component called the spout, and this is the one that keeps all the data in memory, indexes in memory, and allows you to query. And because this is a pub-sub system between the stem and the spout, all the spouts have the full set of data. So this system is built with the idea that you can keep everything you want in RAM. And if you're only storing like 1 kilobyte of data per taxi cab, you can fit a lot of them in not very much memory. So it's basically built to just maximize speed and read everything from RAM. So that's kind of what that system does. Some of the things it depends on. So it uses vibe.d as the web server from Zonke Ludwig, who's done an amazing job. If you guys haven't used the Vibe system, check it out. It also uses pegged from Philip Sigod, which is a grammar-based parser generator. So this is like for analyzing queries and giving you that SQL-like language. And these two things, the S2 geometry library, that's a library from Google. It's a C++ library, about 70,000 lines of code. A lot of languages are converted it. Go, Rust, Python, Java. It's a very useful library. None of them have a complete conversion, except D. And even though other languages have teams of 4 or 5 that have worked on this, well, it took one dude to do this in D, and that's it. Same thing with Avro, just one person. This is one of D's strengths. Because it's such a feature-rich language, things that you consider to be impossible, like, oh, what do I know about this library? I couldn't do this. You just go in, look at the code, convert mechanically, you're done. It's very doable if you want to convert libraries into D. Okay, so let's talk a little bit about the practical elements of like building and deploying these systems in a real environment. I'm using an example of how to actually deploy this because this is a typical setup for microservices. So many of them are built using Docker, and Docker essentially allows you to define like what is my operating system, what's the container in which I run, and you often have to build a build container, which is like you don't actually have your physical server. I'm using something like AWS, and I want them to build it, but what do they build? They don't know how to compile your software. So you have to tell them, like, what does the operating system look like? So in this case, I'm using a distribution of Linux called Alpine Linux, which is very small. It's like 5 megabytes or something. You can put a decompiler on it. In this case, I'm using LDC, and that's it. And there's not much else to it. A few compatibility libraries, and that's it. The next bit over here is the pipeline. There's many ways of building. You can use Jenkins. You can have your own build server. In this case, I was aiming for minimal cost and maximum efficiency. So I used AWS Code Pipeline. And this is one where you don't actually maintain a server. You tell AWS, this is what I want the build environment to look like. It'll set it up for you, build it, and just run it on demand. When I'm not compiling something, I'm not paying for resources. So in this particular case, the build environment has things like, there's 3 types of containers I want. The environment to compile my D program, an environment to run D programs on, which is stripped down and doesn't have the compiler, so if people hack your computer, they can't use anything, and then that runtime environment for the individual project, and you probably have lots of projects in your company. So in this particular case, you have a configuration for code build, and what you basically do is you just give it instructions. What do I need to do? I need to start Docker because the output of my build is uploading a container to, I've compiled my project and I upload it to a container registry in AWS, and that's all it really does. A lot of gibberish here, but the important part is commands you already recognize. Dub build, dub test, and then you just upload. I give it a Docker tag, push it, done. An example project is this one. So I happen to be running, I just make a directory called service, and I already compiled the program. In this case, it's called funnel-mouth. Just copy it over, and then the entry point in my container is I just boot up, run the program, that's it. This is a little bit more of that description here, which is not important, and we're low on time. I wanted to talk a little bit more about deployment. And that structure that I was just running through right now is you have your code in GitHub. Each repository, when you have an update to your code, it triggers AWS Code Pipeline. It runs, compiles your code, uploads an image to Amazon ECR in this particular case. And then at this point, I can actually deploy it. I happen to be using this system called Amazon ECS, or Elastic Container Service. Now there's choices. A lot of people run on Kubernetes. Some people use AWS ECS, and some people use Azure. There's a bunch of systems that are out there. I want to talk about this one in particular because you always have to think about pricing. One of the advantages of this system is that there's no base price. If you're not running containers, you don't pay anything. If you're running on Amazon a managed Kubernetes service, there's a base cost of roughly $72 a month. So especially for small companies, this makes a big difference because $72, maybe $72 you don't have. And so the idea is basically use the right tool for the right job. If you have a dedicated DevOps team that can manage a big complex Kubernetes configuration, great. If you don't, there are other tools that are out there. One tool that I've been experimenting with lately is Amazon CDK, Cloud Development Kit. One of the things that's interesting about it is this, you don't have to read the whole thing, but the important thing is you're writing your configuration for your infrastructure as code. So I'm including things like I'm creating a code as a container, I'm creating a load balancer, I'm saying what image I want to run. And the advantage of running it as code is your editor. You can use code completion. You can look up the documentation from your editor. So like all the trouble you may have had of using Kubernetes and looking up stuff from the manual, it's a pain in the butt. And if you make an error, it takes a long time to discover your error. So having your IDE help you makes a big deal. And this is an example configuration using Java. All it's basically doing is it's creating a service. I'm specifying some parameters. What's the name of it? What's the URL to authorize JWT tokens? What is the URL prefix that leads to this server? So a few functions can actually make deployment a lot easier. So in conclusion, I want to say that D can deliver significantly higher performance and lower costs because it's a high-performance system-level language and uses a lot less resources than languages like Java, Python, JavaScript, etc. It's very feature-rich, which means it's very suitable for bringing in libraries from other languages, and it has a good balance of features to speed up programming, like garbage collection, unit testing, and without sacrificing much for performance. However, D suffers from a small community and needs some additional tooling to kind of help it along, but it has all the elements it needs for success. Thank you.
All right, raise your hands. We've got to have some questions here. Up the back there.
Yeah, so you mentioned that AWS, for example, doesn't have libraries for D, but it has libraries for C++. So just going back a couple of talks previously, Matthias talks, can we not just use the C++ bindings in D and use those?
I haven't tried them, and probably yes, although I hadn't seen that presentation when I wrote these slides.
All right, who else has a question? Down there.
So you mentioned running multiple services on the same machine in order to avoid overhead, but as far as I can see it, the big machine is still going to have to handle all the load that you would have gotten even if you split it up between multiple virtual machines on the same machine. So I'm not really sure what you gain at that point.
Well, there's two kinds of split ups that you basically do. The first split up you do is allowing multiple machines to run on the same computer. But then what happens, you can specify how much resources to allocate to each one of them. So in this particular example, we could fit 2 Java servers in the same computer based on their actual needs in terms of CPU and RAM. And you can actually run performance tests, see how much they need. But the idea is that you can split up a computer more if each process just uses less.
Yeah.
And if you take a simple comparison between like Java and D for a very basic web service, I think I have a table of the resource usage. Here we go. This is just a bare bones web service, like in terms of RAM and like CPU cost. So imagine my input to my company is 5,000 requests per second. Well, I could allocate the whole CPU for that if I was using Java, but I only need half if I was doing it in D. You see what I mean?
I mean that, can you go to the other slide that showed a moment ago?
Sorry.
Yeah. So you're basically running the same service twice on the same machine, and then you split it further. Wouldn't just running it once with all the resources make more sense?
So in this particular case, I happen to be using 4 of the same. And if it scales up appropriately, then you're right. You can just have 1 and you run perfectly fine. But I guess I should have titled this a little better. These are meant to be different services. So, I just have a fleet of computers, and then I have a bunch of different services that I want to run. That's my mistake. I should have labeled them differently in the slides.
Okay, now that makes a lot more sense. Thank you.
All right, that will be it for question time right now. Thank you again, Vijay. That was a good talk.
Yeah, thank you.